Okay, let's start with this lecture. Uh, the lecture that we recorded with the other class is ended up to this section 4.2. So that's why I shared that lecture on the WhatsApp group and I told you that you have to watch that lecture until this one. So this section 4.2 is covered in that video lecture. Because the content of the course is too much and I have to cover in this 11 weeks. So this is the best strategy which I can use to save my time. Uh, Otherwise, I will not be able to complete these 7 COs because one CO is removed from your course curriculum on my request. So that is now you have 7 COs because a teacher can remove only 10% of the course contents. So out of 8, I can remove 1 CO almost. So that is which I already did. So now we have 7 COs, but still 7 COs are a lot for this 11 weeks. Anyhow, this utility that we have, that we can record the lecture and it is the classes are same. So I am using that utility and I am just trying my best to cover the whole course. So this section 4.2 is covered in that video lecture. So you can see them by yourself. It's not difficult. It is integer representation is about we can represent integers in binary form, octal form, decimal form, hexadecimal form. So there is some kind of formula here, which is the representation formula. And then if you have 2 binary digits, then you can add them, you can multiply them, you can divide, and you can take a remainder of them. So these are the simple things, and you already know what these things are because you have studied a course that is called Fundamental of Computers are like that in your first semester maybe. And then we have the modular exponential. That is something different. It is first time you are seeing you. So b raised power n mod m. So how we can find the solution for that? This is the algorithm which I explained in that lecture. And then here on this example, we are applying that algorithm and we are calculating this final result 36. So you can see these things in that lecture. And then these are the exercises that you have to do from at the end at the end of each section in the book. In the textbook, these exercises are available. You have to search them and then you have to provide the solution for them. And now the section 4.3. This section 4.3 is about primes, greatest common divisor, GCD, and least common multiple. I'm sure that you know the definition of prime, the GCD, and the LCM. But today, if I ask you the definition of prime, what would be the prime definition for the prime? Prime number. How you can identify that this is a prime number? Divide by? That is one property. It is divided by itself. That is one property. Or 1. So this is your definition. And then if I say to you that what is the number 1? Prime or not? But according to the definition of prime, now that you will see that 1 is not included in that prime number. So now you will get the updates, okay? Because why I quoted this example? Because you have that fundamental definition. That is okay. That is okay. No issue with that one. But now the things will be updated. So now we have the prime numbers. Then we will see the GCD, which is the same which you already studied in your 3rd and 4th classes, maybe in mathematics, and LCM. So prime definition. So where is the pointer? Yes. So if we are given with some integer, if we are given with some number, and if that number is p, and if it is greater than 1, so this is now the condition, greater than 1. If that number is greater than 1, then now the definition is same. Then now the definition is same, greater than 1. So if you are given with some number or integer, and if we can represent that number with p, and if it is greater than 1, then this number would be prime if it is it can be divided by p or 1. Okay, p means itself and 1 means the number 1. So that is the normal definition. And now your definition is now updated that the number should be greater than 1. And if you are given with some integer again, if that is p and that is greater than 1, and if you are finding that that number is prime or not, and if that number is not prime, then that number is called composite. So this is the definition of prime. So the opposite of prime is composite. Opposite of prime is composite. And now we have the statements of two theorems related to this topic. And the first theorem is saying that we can represent any integer greater than 1. So we are in the topic of prime, so you can expect the statements related to primes. Related to primes. So every integer greater than 1, 2, 3, 4, 5, 6, whatever, you can represent that integer simply as a prime, as a single prime number, or the product of two or more primes. We represent the set of integers with z. You know that. So every integer in that set greater than 1, you can write them uniquely as a single prime number or a product of more than 2 or more than 2 prime numbers. You will understand. In this example, you will see this definition of theorem 1. Okay? And then you will get that understanding. For example, this 7007. So find the prime factorization of this one. So here you are seeing 7 multiplied by 7, 11. So all are prime numbers. And here we have more than 2 prime numbers. So this number, integer, we can represent as the product of 2 or more primes or as a single prime number. And then we have another theorem, and that theorem is saying if n is a composite integer, what is composite integer? Which is not a prime. What is composite integer? Which is not a prime. We have seen this definition here. If you are given with this number n, so if n is a composite integer, then n has some prime divisor. So then that number n, which will be given to you, that will have some divisor. That divisor would be prime, and there is a condition, and it would be less than or equal to n under root. So if you are given with a number which is not a prime, and it is asked to find the prime factorization of that number n, then what is the solution? You can directly find the under root, and then you can see that it would be less than that. It would be less than or equal to that. You don't have to find beyond that limit. What would be the result of n under root? You don't have to find some factor. Factor means, for example, if this is the n and this is, and you have to find prime factor of this one, so you will start with 2. 2, you can divide this number with 2. If it is, then 2 is a factor of that one. Okay, then 2 is a factor of that one. So now if n is a composite integer, so then we can find the prime divisor or prime factor of n, and that factor would be less than or equal to n under root. N under root. So just keep the statements in your mind, or keep the understanding of these two statements in your mind, because these concepts can be used to solve different questions. And now we have example. Find the prime factorization, and some number, some integer is given to you, 7007. So we have to find the prime factorization. Prime factorization means what are the different numbers for this 7007? What are the different numbers through which you can divide that number? And you have to start, and there is a condition written in this theorem 1 that the prime factors would be written in non-decreasing order or size. Non-decreasing mean ascending order. Increasing order, you have to start from small number and you have to go up to the greater numbers. So then it means that you have to start with 2, and then 3, and then 4, and then 5, and so on. And then you have to check that that number is divisible or not. So now we have this integer 7007, and we have to find prime factorization. So according to theorem 1, this number can be represented as a single prime number, or can be the product of 2 or more prime numbers, and we have to represent those prime numbers in order, in increasing order. So what you can do, so here in this example, the approach to solve this problem or solve this question is very much simple, like third and fourth class. So you have to start with 2. If it is divisible by 2, then good, take it. Then you have to check the next prime number. And if it is divisible, take it. And then you have to check the result. For example, here may be. So we have to perform the division of 701 with successive primes. What are the successive primes? Just start from 2. I'm not asking. 2 is a prime number. 3 is a prime. 4, no. 5 prime. 6, 7 prime. 9. 11 is prime. 13 is prime. So these are prime numbers in a sequence. Successive primes. This is called successive primes. So you have to divide this number successively or in a sequence with the primes. You have to start with 2, and then you will get some result. If it is divisible, then you will get some quotient, you can say. And then you have to take that quotient and divide it again with 2. If it is divisible, okay, take the result. If it is not, then try the next prime number, which is 3. And in this way, you can go on. So here, 7007. So first we are trying to divide it with 2. So check it. So due to this last 7, so we know that this is odd, this is even, so it is not dividable. So leave this one. So 2 will not give us some results. And then try with 3. Maybe, I don't know, maybe 27 will come and then 3 multiplied by 9, you will have 27. So you have to check. So 3, 2, 6, and then 1 is going forward. 3, 3 is a 9 and 1 is going forward. 3, 3 is a 9 and 1 is going forward. So finally we have 17. And 17 is not divisible by 3. So leave it. Check this 5. 5, 1, 2 is remaining. And 5, 4 is gone. And then this 0, 7 is not divisible by 5. So that's why 2, 3, and 5, they are not dividing this one. So then what? Now we are going to check the next one, which is 7. On 7, it is clear. It is divisible. It is divisible. So it is divisible. So keep this. So 7 divided by 7. So this is the quotient. So this is the quotient, 1001. This is the result. So now keep that only 1 7 in your record. And try that quotient again with 7. When you will divide it, 7, 3 will go forward, 28, 2 will go forward, 21, and with 7 it is divisible. So with 7 again, you are going to divide that one, and what the result you have? Maybe 7, 1, and then 2, 4, 1, 4, and 3. 1, 2, 3. 1, 2, 3 would be the result. 143. 143. Okay, good. 143, yes. 143. And then 143, you have to divide it with 7. If it is not, then it would be divisible with 11. Okay? Yes, result. Quotient. 147 would be divisible by 11. And then whatever the result would be, that would be divisible by 13 finally. 30. So now these are the factors that you, prime factors. These are the prime factors for this number that you have found now. You can further write it as there are two 7, so 7 square dot 11 dot 13 by theorem 1. So this example we have solved by using this concept of theorem 1. Yes.
So we start from 7. 7 divided by 7. So I should go to the bigger number.
No.
I start from
you have to start from the beginning because this condition is written here. When the prime factors are written in order of non-decreasing size. So you have to pick the prime number in ascending order, in increasing order, from 2 to onwards. From 2 to onwards. Now, there is another theorem, and the statement for that theorem is in these lectures, I presented many theorems, not always all theorems we are using in the questions, but maybe in your exercises. Okay. So if you are doing exercises, then you have the answer of this question. If you are not, then okay. So you will use these exercises. For example, you will use these theorems in the exercises. Okay. Theorem 3, there are infinitely many primes. Okay. If so, that is okay. 2, 3, 5, 7, 11. We don't know, and so on. We don't know because this set all numbers is infinite. We can go on and go on. So that is simple. That is simple statement. Yes, we are agree with this statement, theorem 3. And then there is some other name for prime numbers that is called Mersenne primes or Mersenne primes. And what are the Mersenne primes? To understand this one, first we are going to see this equation 2 raised power n minus 1. And if we will have the value of n, then we will have some number finally after evaluation of this equation. So 2 raised power n minus 1, we are saying that it would not be a prime when this n is not a prime. In this equation, we are going to say that some number in this form would not be a prime. So the condition is cannot. It means that it can be a prime also. It can be possibility. There is a possibility. There is no any word here that 2 raised power n minus 1 is not a prime when n is not a prime. There is no verb is. It is cannot. When there is a verb cannot, then there is a possibility that it can be a prime. You will see. So 2 raised power n minus 1 cannot be prime when this n is not a prime. So if this n is not prime 2, 3, 5, 7, 11, if that is not, then this whole thing is not a prime. So for example, here 2 raised power 2 minus 1 is equal to 2 raised power 2. If this 2 is prime number, 2 raised power 2 minus 1, so this 2 is a prime number. If it is a prime, by this statement we are saying that if n is a prime, then this can be a prime. And if n is not a prime, then this cannot be a prime. So this statement has this understanding. This statement has this understanding. Now, and who gave this theory? This is the name of a person, French monk. Monk is something, the persons who normally lived in church, you can understand. And they have, his name is Marin Mersenne. And due to his name, this is called Mersenne primes. So he's saying that this 2 raised power n can be a prime and cannot be a prime. And who defines this? This n. If n is prime, then it would be prime. If n is not a prime, then it cannot. Let's see some examples. So 2 raised power 2 minus 1. So this 2 is a prime number. So if you calculate it, 4 minus 1 is equal to 3. So this 3 is a prime. And this n is a prime also. So up to this point, this is okay. This Mersenne is saying the right thing. Then 2 raised power 3 minus 1. This n is a prime. So 8 minus 1, you have 7. So this is also a prime. 2 raised power 5, which is 32 minus 1, it is 31. 31 is a prime. Okay. 2 raised power 7 minus 1, which would be 127. It is a prime. So all these things which are written here, these are called Mersenne primes. But this number, 2 raised power 11 minus 1, so this n is a prime. This n is a prime number. But when you calculate this, it would become 2047, which is a product of, which is a multiple of 23.89. And prime normally don't have any multiples. They can be divided by itself or 1 according to your definition, greater than 1. But this 2047 is divisible by 23 and also 89. Because when you will multiply them, you will get this 2047. So here it is not a Mersenne primes. So that's why the word is cannot. And this theory is only a theory. It is not something theorem, okay? That's why it is not something proved theorem. Otherwise, this is a counterexample to negate that theory. So his statement, his Mersenne statement is now negated with this counterexample. So that's why it is only a judgment. It is only an observation of that person, and he just gave that his theory. Theorem 4. The prime number theorem, the ratio of the number of primes. When there is a word ratio, then it means you can understand it would be in a kind of fraction or like that. The ratio of number of primes, you have to calculate number of primes. Not exceeding x, x will be given to you. Not exceeding x and x natural log of x. That will be approaches to 1 when the value of x will be increased. The meaning of this one is that one. That the prime number theorem tells us, it informs us that the number of primes not exceeding x, if some number will be given to you within the limit, and you have to find the number of primes, how you can approximate, calculate this formula. That number divided by natural log of that number. And then you will have that value. It's a theoretical discussion. Read it from the book. It is written here with some little examples. That number will be given to you. You will put that number in this formula, and then you will find the natural log of that number. The result is simply the answer of that ratio. Definition 2. Now we are moving toward GCD. Now we are moving towards GCD. In the previous class, I have given an announcement that I have taken the vote from all of this class, and mostly students gave this vote that in the midterm, we will not have the theory. We will only have the questions, the problems. For example, find this one, like that. For example, the questions like that, find the prime factorization of 7007. And you have to calculate it mathematically, mathematical stuff. And all examples are included, and all exercises like this one are included, and all the homework and quizzes, whatever you have, that is included. But I will not ask what is the definition of prime, what is not the definition of composite, what is the statement of this theorem 1 or theorem 2. You must have to know that. If you have that understanding, you can solve this question, otherwise you cannot. Yeah, this is the course in which we have 2 midterms. And we are just, this is not. Okay. Should have. This is good that you have reminded me, otherwise I was going like that. Okay. And at the end, it would be an issue for me. Okay. So, okay, up to CO3, we will take the midterm 1, and maybe after the midterm, maybe passing 2 weeks after the midterm, then we will have the midterm 2. Okay. So GCD, what is GCD? Greatest, the word is greatest common divisor. You will be given 2 numbers or maybe 3 numbers, but normal definition is with 2 numbers. And the name is greatest common divisor. You will be given 2 numbers, A and B, and you have to find the divisor of those 2 numbers. One divisor that will divide number A and also divide number B. You have to find that single number which can divide A and B commonly, but it would be greatest. It would be greatest. Otherwise, there are many other possibilities, but it would be greatest. So that is the normal definition that we are seeing from our early childhood classes. That is the definition of that GCD. So here, we will be given with these 2 numbers, not both 0. So 0 numbers are not possible, okay? Only integers. And the largest integer d, we have to find some greater in our largest integer d, such that this d will divide a and this d will divide also the b. And if it happens, then this is called GCD of AB. And you can represent it with GCD into A comma B in mathematics as we are doing. For example, this is simple. For example, what is the GCD of 24 and 36? So you can, again, there is a procedure given to us in early classes that there you have to find the multiples and then you have to find the commons and then multiply them and then you have the final result. Otherwise, you can take the smallest number from them, 24. It's just a shortcut, but it is not accurate always. Take the smallest one. Okay, this is 24. Make it half and then you will reach at that point. Most of the time it will give you the result. Or sometime, but this is not accurate. You have to find one by one from 2, 3, 4, 5. But at least you can take the smallest one and check that smallest one, that this smallest is a divisible of that other one. If it is, then that is the GCD. So you have to come in a downward direction from that smallest number, and then you have to check that it is that this number is divisible and also this number is divisible, then it's okay. So that is the shortcut. So this is a very common and simple thing. Now we have another definition, relatively prime. We will use this concept of GCD in some other dimensions. As a GCD, we are not going to do this GCD for the third, fourth class that you already did in your early childhood classes. We are not going to find that GCD again, but this concept now we are going to use in other things. So now we have the definition. What is relatively prime? So you have seen what is prime, but now we are going to see what is relatively prime. So if you are given with the two numbers A and B, and if the GCD of those two numbers A and B would be 1 and not anything else, then those two numbers A and B would be called relatively prime. Okay. So now you are going to see how the concept of GCD is being used in some other things. So what is relatively prime means? If you are given with two numbers or more than two numbers, here this is simple definition. So that's why it's two numbers. Sometime we will, the other extended concept is pairwise relatively prime. Here you have more than two numbers, okay? So in this definition 3, you have only two numbers, A and B, and you have to find that they are relatively prime. Then what? You have to find their GCD. If their GCD is only the 1, then they are called relatively prime. And for example, this is the example, 17 and 22. These two numbers are given and it is being asked that they are relatively prime. You have to find their GCD. If their GCD is 5 or 7, then they are not relatively prime. But if their GCD, only GCD is 1, then they are relatively prime. Definition 4. What is pairwise relatively prime? Pairwise relatively prime. Here in this case, you will be given with more than two numbers. More than two numbers. Here in definition 3, you are only given with two numbers. In definition 4, you will be given with more than two numbers, A1, A2, and so on, AN. And then what? You have to make their pairs first. A1 with A2, A1 with A3, A1 with A4, A1 with A5 and so on. And similarly then A2 with A3, with A4, with A5, like permutation that you already did in your earlier classes. So you have to make pairs and then you have to find their GCD, and if it is 1, then they are pairwise relatively prime, because the definition of relative prime is GCD is equal to 1. So pairwise you have to make their pairs and then you have to check that they are relatively prime or not. For example, here you are given with 3 numbers 10, 17 and 21. So make their pairs 10 with 17, 10 with 21, and then 17 with 21. Alas, for these 3 numbers, all the pairs are now in an ascending order. You don't, if you just go in the front, if you say 21 and 17, this is the same 17 and 21. So you don't have to repeat that. So then after making the pair, we are now checking their GCD. GCD of 10 and 17 is 1. GCD of 10 and 21 is 1. GCD of 17 and 21 is 1. So now their GCD is 1. So now you can say that this 10, 17 and 21 are pairwise relatively prime. All the pairs. Okay. Definition 5. LCM, least common multiple. What is the multiple of 6? What are the multiples of 6? You can say 2.3 are the multiples of 6. Or 2 is a multiple of 6. 3 is a multiple of 6. Anyhow, least common multiple. Least, the most smallest one. Okay? Least means the most smallest one, not the greatest one. The most smallest. And common. It means here we are again giving with 2 numbers, and then we have to see something common between them. That would be smallest. That would be smallest. Least common multiple. If we are 2 numbers, we are given with 2 numbers A and B, then LCM would be the smallest positive integer. Smallest positive integer that is divisible by both A and B. That smallest positive integer would be divisible by A and also by B. Not A and B are divisible by that smallest. Rather, that smallest number can be divided with A and also with B. Okay, it is just an opposite direction. You don't have to divide A with the smallest. No, you have to divide that smallest number with A, and then you have to check with B. And if A and B both are dividing that smallest number, then that smallest number is called LCM. Okay, that called LCM. And we can represent it with LCM A comma B. And now we will mix the concept of prime factorization and LCM together. We will use this concept of prime factorization to find the LCM of 2 numbers. So if you remember that previous prime factorization here, this one, non-decreasing order, increasing order, or ascending order. So if you will be given with 2 numbers and you have to find the least common multiple, LCM of those 2 numbers, then you have to find their prime factorization. And if this P is a And if you have the prime factorization of A and also prime factorization of B, for example, this is the prime factorization of A and this is the prime factorization of B, prime factorization. It means 2 is coming 3 times, 3 is coming 5 times, multiplied with 7 is coming 2 times. And then what is the number? That is some whatever it is. It is the prime factorization of that number. And the question is, what is the least common? What is the LCM of this number and that number? This is A and B. So what you can do now to find the LCM? This 2 and this 2 which is here, which is common. So you are writing with that 2 with representing that 2 with P. So this P is prime factorization. This P is prime factorization. P, and so on. They are multiplying with each other. And what you have to do, for example, here the power is 3 and here the power is 4. So you have to write 2, then max, here 3, comma, this 4. This one is A1, this one is B1 or whatever you want to say. These are A1, A2, A3. These are B1, B2, B3. Similarly, if you have another number, C1, C2, C3. So this 2, it's easy, but this is the formula. So you have to keep that prime factorization. You have to keep the same things together, and then you have to find them. You have to keep the maximum between their powers. What is the maximum power of 2? 4. What is the maximum power of 3? 5 and 3. What is the maximum between 2? 5. Which you are keeping. What is the maximum of 7 square? Here you don't have 7 0 here. So 7 2, okay, keep that 7 2. And that would be the LCM. So this formula is saying that keep only the maximum of A1 among A1 comma B1. Similarly, for second digit, this is for second digit. Similarly, if you have another digit and so on, n digit. So if this is the first number and this is the second number, and we are going to find the LCM. So according to that formula, you can convert it to 2, that is 2. And here we have 2, then apply this max. And what is A1? This is A1. Write it here. What is B1? This is 4. Write it here. And what is the maximum between them? 4. Keep it here. And similarly. So this is the simple one. Now, we are moving toward an algorithm that is called Euclidean algorithm. Take a 5-10 minutes break and then we will start again, because 2-3 students are already gone. Take a 5-10 minutes break. Allah. So now we have the Euclidean algorithm. This algorithm is basically a better solution for finding the GCD, because previously when you are finding the GCD with prime factorization, so in prime factorization you have to check the first prime, it is the prime or not, and then you have to find the quotient, and then you have to divide with the prime, and you have to check it again and again by hit and trial method. So it is a time-taking process to find the prime factorization. So, but finding GCD with this algorithm, it is a little bit better solution, it is an efficient solution. When there is a word efficient, it means it will take less time. It is a better solution to find the GCD with Euclidean algorithm. So for example, here, this is algorithm 1, Euclidean algorithm. The procedure is given there, which is quite simple. The name of the procedure is GCD, and we will give two numbers, which would be positive integers. And then we will store the first number in a variable x, then the second number in a variable y. And then we have a loop, and this loop will continue until your second number y will not become 0. Okay? Until the value of y will not become 0, this loop will continue. And these three statements are under this loop. And in the first statement, we are dividing this x, which is the first number a, we're dividing this x with the y, but we are taking mod. And when there is a word mod, then it means modulus. It means that we will keep the remainder of this division here in this R. Okay? We will not take the quotient, we will take the remainder. When there is a word, mod is there. The quotient will not come into this R, rather the remainder will come into this R. Now, after keeping this remainder value here, now we are going to update this second number y into the variable x, which is the first variable. So we are updating second number in the first variable. And then we are updating this remainder. We are updating this remainder in the y variable, which is for the second number, b. So we are updating. We are updating the values that now, previously the second number which were given to us, now it is becoming the first number, and the remainder that we got in the previous step is now becoming the second number for the next division. Now, and then this will go on and go on until this y, when the value of this y will become 0, you will come out of this while loop and then return x, and the value of x will be returned. And this x would be the GCD of A and B. It's easy to understand. You can take, for example, you can take 4 and 6 here to find their GCD, and then you can process them. But here we have an example, so we will see that example. But this is the understanding. For example, 4 and 6 will come here, and 4, okay. 4 mod 6, this is you cannot do. When two numbers will be given to you, you can keep the first greater number in here in x and the lesser number in y. This is the condition also. Okay, so if I will give 4 and 6, then what you can do? You can keep 6 here and 4 here and 4 here. You can keep 6, the greater number here, and 4 in y. Now your x is 6 and y is 4. So y not equal to 0, condition true, and then 6 divided by 4, you will get what? 2. So r is now 2. And now 4, your x is now 4. Your y is now 2. Okay. Y 2 not equal to 0? Yes. And then what? 4 divided by 2? And you will get 0. And then your x is what? 2. Your x is 2 now. And your remainder is, your y is 0 now. 0 equal to 0, condition false, return x. What is the value of x? 2. So 2 is the GCD. 2 is the GCD. Anyhow, leave it. You got the understanding of this algorithm. By the way, I can also write an algorithm for you, but I will not. Okay? But I will not. Because these are the quite easy algorithms. This is not difficult. Okay, we have another lemma. Lemma is what? What is the meaning of lemma? Like corollary, lemma is also some kind of effect which is bigger than corollary, okay, but less than theorem. A small proof, you can say. So, for example, here we are supposing A is equal to BQ plus R. What is this equation? What is this equation? All students. What is this equation? We have seen this equation before. Hmm? Innocent. What is this equation? What this equation is saying? This is equation where A, B, Q, and R are integers. We used this thing in previous slide. For what purpose? To get the remainder. So this R is a remainder, this Q is a quotient, and these are two integers, A and B. And if you divide A with B, then B will multiply with some quotient. And if there is a remainder, then plus remainder, then that side will be equal to that A. That is that equation is saying. So if this is a equation, then GCD of AB is equal to GCD of BR. This is something which is already proved by some person, that GCD of AB, if this holds, then GCD of A and B would be equal to GCD of B and R. B is the second number, R is the remainder. Okay, anyhow, keep this in mind. And now we have this example. Find the GCD of 414 and 662 using the Euclidean algorithm, not the similar method that you got from your childhood classes. Use the Euclidean algorithm to find the GCD. So the question like that, it can come. It can come in the quiz or homework or whatever. So if you know what is Euclidean algorithm, only then you can solve that question. But if you will solve that question with the concept that you got in your childhood classes, then answer would be wrong. I will give you 0. Okay. Okay. So for example, here, what you have to do, you have to start again. So this is the bigger number, this is the smaller number. You have to use this Euclidean algorithm. And here it is written in practical form. So 662 is equal to, this is the second number. We are using maybe this equation, you can say, but not, we are using this, actually the Euclidean algorithm. So this is the number which we want to divide with this 440. Here 441 multiplied with 1. When you divide this 662 with 414, if you multiply it with 2, it would become greater than this one. So that's why it is multiplying with 1. So when you divide it, this would be the remainder, 241 from this 662, okay? So we have the remainder, we are getting remainder, and we are getting x and y. So here this is, okay, if this is x, this is y, and this is r, according to that concept which is written here. But we are writing here. So this is the first step. After dividing this 662 with 414, and what is the quotient? 414 multiplied with 1. You will get 414 here, and then after subtraction, you will get 248 as a remainder, which is written in this equation, in this form of equation. And then what? Okay, this is the first step. Then the loop is still going on. So for the next step, so this is my y, which I am making it as x. And this is my remainder, which is I am making as y. So now I am dividing 414 with remainder 242. So 414 is equal to 242, 248. And when after division, you will get 166, the remainder. So now this is again the second pass of the loop is now gone. And now in this step, this is my x and this is my y for the next step. You have to divide this 248 with 166. So then what? 248 is equal to 166 multiplied by 1. And then what is the remainder? 82. This is my x now, and this is my y for the next step. So 166 is equal to 82 multiplied by 2, and this 2 is the remainder. This 2 is the remainder. Are you getting what I'm saying? Just raise your hands, the students who are understanding. If you will not give attention now, you will not understand it. Keep this in your mind. Maybe you will pick some points, but not totally. This is mathematics, okay? So anyhow, so now we are here. So this is my 82 is my x, and this 2 is my y for the next pass of the loop. So now 82, now you are dividing with 2, 4 multiplied with 41, then it is equal and the remainder is 0. Y is 0. Now the remainder, now y becomes 0 and you will come out of this loop. And where is the solution? Solution is here at this statement, the remainder is 0. You have to go back to the previous step where remainder is not 0. Here, remainder is 2. So that previous step is basically giving you the GCD. So this 2 is now the GCD of this 410 and 62. At this step, the remainder is 0. The remainder is 0. Or you can say you have to go back where the remainder is not 0. And then what? You have to find the value of x. You can understand. Or you can go back and yes, that is okay. You have to take the value of x, not the value of r, not the value of remainder. So you can say like that, or you can say, so the last non-zero remainder, because 2 is the last non-zero remainder, or you can apply this Euclidean algorithm. So you can go back. So now there are two concepts. When y is 0 means remainder is 0. So here at this step, the remainder is 0, and then you will come out. And then you will come out. Yes, the remainder is 0, and then you will come out. The value of r will be y, and then y checked. So this is the statement, not the previous one. This is the statement, because next time it will be checked and it will come out. And then here, so now here the first value is 2. So this is my x, and that 0, which is not mentioned here, it is better to mention that, then you will not confuse. So this is my last non-zero remainder. This is my x, and that x is the GCD. And then you can write GCD of this 414622 is equal to that value. That one. Sorry, this is not that one. This is this one, okay? According to this algorithm. Now,
when I solve it, I should write like this or
like this. Or you can write. Now you are saying, now you are going to move to these algorithms. So that is the reason That is the reason the teacher always gives theoretical portion and also the mathematical stuff. Now you see that this algorithm is better with this approach. So now you are demanding this one, but this is not good now. You have to go with like that one. You can go with the algorithm, okay? No issue. No issue. You can go with the algorithm because basically the concept is same. The representation is different. Representation is different, but actually the concept is same. What is the word for representation? Numaish? Huh? Tamsil. Okay. This this one is confusing. It is the difference of tamsil. Here in algorithm, it is up to you. It is up to you. You can write this algorithm and then you can write the values separated with commas. And finally, you have that GCD. I will check only your maybe because I have to check many papers. So what I will do, I will just give a look and I will take look at the answer. And it's okay. Because the question is not too much, and with more than 20 years of experience now, we can check without just look. Oh, there, oh. So now we have another theorem which is called Bezout's theorem. Bezout's theorem. And what this theorem is saying, it is again saying the same thing. If we have two positive integers a and b, then there are some other integers s and t would exist, and then you can write this thing with those variables. That GCD of AB would be equal to SA and TB. This A and B is the same integers that would be given to you, and this S and T, those would be the new variables or values that would be introduced by you, and it is becoming multiple with A and with B. It is multiplying with A and B, these new variables S and T. For example, and this is the example to understand this Bezout theorem, express this GCD. Now the question is this one, the GCD of these two numbers A and B is given to you, which is 18. So GCD of this 252 and 198 is 18. Express this GCD. And what is the question now? This second part will clear. Express this thing as a linear combination of 252 and 198. Express this GCD as a linear combination of A and B. So the question is express into the form of linear combination. This is linear combination. Okay. When you have this something like that, you will again use maybe Euclidean algorithm. Okay. You will again use. Express that GCD as a linear combination of this A and B. So we will again so this is the GCD 252 is equal to 198 is equal to 18. So here the GCD, the answer is given. This is the final answer. If you will perform Euclidean oval algorithm to find the GCD of these two numbers, then this 18 you will get at here. At the end, at the last steps, you will get 18 something here. So what you have to do to find these linear combinations, you have to apply the GCD and you have to open up or you have to display or you have to show all the steps of Euclidean algorithm. Okay, if GCD of 252 and 198 is 18, now we are going to use the Euclidean algorithm again from the start up to the end like this. So 252 is greater, so keep it on the left hand side. 252 and divide this with 98. Divide this with 98. We cannot multiply it with 2 because the value will become greater than that. So it is, we are multiplying with 1. When you do it, the remainder from 252 would be 54. I can move this line here down and then it would be easy for you. But I'm saving my space. Okay, that is the reason I'm putting arrow. And maybe due to that arrow, it is confusing for you. Otherwise, it is not. It is a new line. You can move this on the new line. Then it would be easy for you. So now the first step is now gone. Now this is my X for the next step. Now think over this step. You have to identify things for the next step. So this is now my X for the next step. And this is now my Y for the next step. So that's why I'm dividing this 198 with this 54 here. And after multiplying with 3, putting it here and subtracting, you will get the remainder 36. Everybody is understanding this or not? Just raise your hands. Where is your hand? The last student at the corner. Okay. He's not understanding. Still some steps are remaining, and if you give attention, then you will understand. You will understand. So now this step is gone. I have to go to the next step. For the next step, this is now my X and this is now my Y. So I have to divide 54 with 36. So this 54 is equal to 36. 36 multiplied with 1, 36. Write it 36 here. And what is the after subtraction? What you will get? 18. 18 is the remainder. When you divide 54 with 36, 18 is the remainder. So this step is now gone. What is the next step? So for the next step, this is my X, this is my Y. So I have to divide 36 with 18. So 36 is equal to, I am dividing this 18. 18 multiplied by 2. And my remainder is here plus 0. That is the last step. And for the last step, this is my X, this is my Y. And Y is equal to 0. Euclidean algorithm will come out. So that is my X in the Euclidean algorithm, according to Euclidean algorithm. So that GCD is already given there. We are not solving the question now. We need these steps to solve this linear combination. So that's why we are opening these steps. The actual question is, express this GCD as a linear combination of A and B. For linear combination, we need these steps. So that's why we know the answer, but we now open up all the steps. We have opened up all the steps because we need these steps to find the linear combination. But this is not a linear combination. What would be the linear combination? This is the representation. With the value of A, you will have some value S. With the value of B, you will have some value 2. Then it would be, for example, 18, GCD of AB, 18. 18 is equal to something like that. Then you can say. And these S and T would be called Bezout's coefficients. Okay? If I write 2x plus 3y is equal to 0, then these are called coefficients, 2 and 3. And then for the s, what was that? SA and TB, SA plus TB. So these are now called coefficients. We have to find those coefficients. Actual question is this. So now, using the next to last division, the last division is this one, 36 plus 2, where the remainder is 0. Next to last is this one, or the third division. This is first, this is second step, this is the third iteration of the loop, or the third step. So we are going to use that one. So you have to do the same thing in every question, if the question is like that. Using this step. So actually, why we are using this step? Because here we can move this 1.36 on the left hand side, and it would become 54 minus 1.36 and then is equal to 18, or like that. And then you have to put that thing in the next step, and then you have to put that thing in the next step. We will see. We will see. So here we know that GCD of 252 and 198 is equal to 18. We can express this GCD as a linear combination of 252 and 198. This A is 252 and this is 198. The final form would become like that. You can see 252, 198, and you have something here. So this 252 is your A, this 198 is your B, but these are the coefficients, 2, 4, and 5. These are the Bezout coefficients, S and T. You have to find that. And this is the linear combination. This is the combination. This is the linear combination of 252 and 198 with respect to this GCD 18, because we have these things. So what you have to do, you have to move using this step. We can say that all these steps are equivalent, and all these steps are for this GCD 252 comma 198 is equal to 18. So now by using this step, you can move this 136 with this 54, and you can write it like that. 18 is equal to 54 minus 1.36. Are you getting what we are moving this part towards 54? This part is a positive part. When it will be moved on to this 54, it will become negative. So 18 is equal to 54 minus 138. It's okay or not? We are using this part. So and now this is equal to this one, this is equal to that portion, this is equal to that portion from the start. So all these things are for this GCD 252 comma 198 is equal to 18. So okay, we start with this approach. Now we have 18 is equal to this one. I'm not just mentioning these theoretical portion for your better understanding. Use this last statement and identify something like that. And now I am just highlighting for myself. Okay. So now this 18 is basically the GCD, which was the GCD of this one, 18. And this 54 and this 36 is now the linear combination of GCD, but it is not final. With this B, we have 1, but with this A, we don't have anything. So it is not final yet. What would be the linear combination? I told you when you have S with A and T with B. But here we have with B maybe this one, but we don't have any S with this A. So still something is needed. What is that thing? Then we are moving towards the next step, which is this one. 198 is equal to 3.54 plus 30. What you can do here, move this portion to with this 198. And what it will become? It will become 36 is equal to 198 minus 3.54. Doing the same thing with this second step. Keep this. You can mark this equation as 1. You can make it as equation 1. And now, after doing something with this next iteration, you have 36 equal to 198 minus 3.54. Now, what you can do? We have 36 is equal to this one. We have 36 here. Replace this value in the previous question, in the previous equation. In this previous equation, put this value of 36 here in equation 1. Then it would become what? It would become 18 is equal to 54 as it is, minus 1.36, which was the previous. And now after putting it in place of 36, you will have this portion. 198 minus 34 here, like you can see here. Clear or not? Raise your hand, please, if you are with me. The students who are with me. I am going very much slow so that I also understood and you also understand. No doubt, before coming here, I saw all this stuff for my preparation. I always saw. Otherwise, a teacher cannot go in a good way in the class. But again, it's a mathematics. Sometime you can stuck at any point. So that's why I'm going very much slow. So be with me. So I am just replacing this value of 36 here in this equation 1. And then we are getting 54 minus 1, 198 minus 3.54. Okay. Now simplify it. If you are able to simplify it, then simply this is 3 times 54. This is only 1 time 54, but not mentioned. So 3, so this is when you multiply it, it would become 1 with 198, it would become minus 198. Or you can say minus 1.98, which is written here. Minus 1.198. And this is minus plus, so 3.54. This is 3 times 54 and 1 time this one. It would become 4 times. So it would become 4.54. You don't have to calculate. You don't have to calculate the final result. No, we need coefficients. So keep it as it, but just simple. We need S and T. So now we have, if this is A, we have this S. If this is B, we have this T. But we have to find these coefficients not for 54 and 198. We have to find for coefficients for 52 and 198. Okay. We have to find these coefficients for 252 and 198. Okay, for 198 we have something, but this is not 252. So we have to go up to that point. We have to replace, substitute again and again up to that point. So what we can do next? So here, now we have this one. Now we have this step. What we can do here, move this portion with 252, and you have 54 is equal to something like that. 54 is equal to 252 minus like that after moving it. Okay. And this is what we have here previously. 54 is equal to 252 minus 1 dot. This is, do we have 54 here? Yes, we have 54 here in the previous. So make it as equation 2 if you want. Just to make it as previous equation 2 for your easiness. And now you have this one, 54. Substitute this 54. Substitute this 54 with this value in equation 2. In equation 2. And then you will have what? 18 is equal to 4 dot, and put this value of 54 here. 52 minus 1 dot 198. And then the remaining minus 1 dot 198 as it is. And now simplify it if it is able. This is 1 time 98, and okay. This is 252 4 times, okay. And this is minus 4 and then minus 1. So minus 5. Minus 5 times 198, it is here. This is what you want. This is your A and B. Now your ABs are there. And if you have the AB there, then these coefficients that you have are the final coefficients that you needed for finding the linear combination of 252 and 198. Clear? These are the exercises, too many. Because now I know that you are more focused on exercises. So that's why I have increased the number of exercises from 5 to any size. Okay. This is the last section, not of this CO, but of this section, of this chapter 4. Congruences. The meaning of congruence is what? Agreement. Agreement. And now the definition of linear congruence is given here. And these topics of congruence, I hope that you are seeing for the first time. Only in discrete structure. So linear congruences. So if you have an equation like that, I can also say that if I have a congruence like that, due to this symbol, this symbol is called congruence symbol, okay? In some previous slide, maybe this symbol was already there. And we know that this symbol is called congruence. I can also say that AX is congruent to B modulo N. I can read this equation like that. And in this equation, M is what? A positive integer according to previous knowledge. A, B are simply integers. And X is what? X is a variable. This X is called a linear congruence. This variable X is called linear congruence, or this form, or this complete form. This complete form in which we have this variable X is called a linear congruence. Previously, in the previous slide, we have like that, we don't have any x. We have directly A congruent to B modulo M. We have equation like that in previous slides. But now here we have another variable x. And when you have this variable, then this is called linear congruence. You have to keep it in your mind. And now we have a theorem. Keep this thing, keep this form in your mind, and then read this theorem. If A and M, if this A and if this M are relatively prime, what is relatively prime? When their GCD is 1. Okay? This is the actual thing. I am an old man, you are a young man, you can keep more things in your mind. But you are still testing me, huh? This is the time. Listen, this is the time. You can keep as much information in your mind as you can. But when you will above 40, you will see the difference. I am just saying it to you. We don't have any control. Believe me, we don't have, for example, I don't have any control of my memory. Sometimes things lost and I don't know why. And even I cannot express with the colleagues or friends. Then they will say, this man is Salli Valli. Believe me. So this is the time for you to keep as much information in your mind as you can. Now keeping things in my mind, as my case is, keeping things in is quite hard for me. If I have to understand something, I have to look from the zero up to that point, and then I can understand that. Because that previous information is not existing anymore. So this is the time. Read it if you want to be a successful career, if you want a successful career in your future. Keep as much information in your mind which you can. And it will produce, when you have that information, it will produce good skill in your personality. And those skills will help you in getting good positions in this world. So anyhow, so if this A and M are relatively prime, and what is relatively prime? When their GCD is 1. So it means their GCD is 1. And M is greater than 1. Okay, for prime, we know that. But this, because we are considering them relatively prime, so that's why we are saying that M is greater than 1. Anyhow, keep it as is. Keep as it is saying here. If A and M are relatively prime, then an inverse of A modulo M exists. Or you can simply say that then inverse. Now we are going towards another topic, how we can find an inverse of a congruence. How we can find an inverse, for example, if some congruence is given to us. So that's why you have the words like that. So if A and M are relatively prime, for example, you can see this question, find an inverse of 101 modulo 4620. And here it is A and here it is M. Okay. So anyhow, theorem, if A and M are relatively prime integers, then an inverse of A modulo M, something will be given to you like that, into this form, A modulo M. Then inverse of A modulo M exists. So now there is no can, may, or what. Exist, must, can. Solution must be existed. If they are relatively prime and M is greater than 1. And that inverse would be unique solution for that modulo m. Unique solution. That inverse would be unique. These two lines are necessary. These two lines are enough to keep it in your mind for the future questions. But this is illustration. This is further explanation of these two lines. And what these two lines are saying, there is a unique positive integer. Unique positive integer. When there is a positive integer, then you can consider that there is no negatives. 0, 1, 2, 3, 4. Less than m, which is that modulo m. Unique positive integer less than m, that is an inverse of modulo m. So that inverse, that will be the solution. That would be less than this m. And that would be unique. There would be some solution that would be greater than this m. That is also possible. But there would be solution which would be less than this m. And that would be unique. Less than this m, that is also an inverse of a modulo m, a inverse of a modulo m. And if there are other solutions which are maybe greater than this one, or if there are any other solution, you can call those solution congruent to modulo m. Anyhow, keep only these two solutions. If two numbers a and m is necessary because it is modulo. So if a and modulo is given to you and it is said to you that they are relatively prime, even if they are not said that it is relatively prime, and if it is said that a something is given to you into the form of this one a, and if this is m, if something is given to you a modulo m, and if it is asked find an inverse, that is the theorem now. Find an inverse, you have to remember it that this is that the form of equation a modulo m, and we have to find the inverse. And how you can find the inverse? Again, two steps: Euclidean algorithm and the Bezout's coefficients. Things are getting complicated when you will go forward and forward and forward. I can skip these things, but I don't want to. I am also doing some inner competition with my memory. I don't want to share, but actually from my inside, I can skip and you will not know anything. But I'm not going to skip it. I want to fight with these concepts. So anyhow, so again, you have to use the Euclidean algorithm and the Bezout's coefficients. Because one thing, if I will not use my memory, then everything will be lost soon. Yes. Time is up. Okay. I will try to record this lecture. I will try. How many weeks are left? Maybe 5. Maybe 5. I think. So that thing is in my mind. And if something happened, I will record these lectures at home and I will share those lectures with you. And then you will say, Allahu Akbar, Allahu Akbar. Okay, I will start here again from this example 11.